But yeah, it is 1 p.m., so we can go ahead and get started. So welcome everyone to the second day of the MTV Nuclear Engineering Summer School. I'm Flynn Darby. I'll be moderating some of the lectures here and providing one later in the series. But I'm happy to introduce you all to Patrick Park, a PhD student from Princeton University, who will be talking to us today about historically the German reactor program during the Second World War. Um, Also, he does quite a bit of other research. He works more specifically on satellite monitoring, specifically with North Korean nuclear programs, but very excited to hear his historical talk today. With that, Patrick, please take it away. Looking forward to it.
Thank you for the intro, Flynn. I'm Patrick, and today I'll be talking about some of the nuclear forensics work that I did with the German nuclear program in World War II. And this was largely a collaborative work between people at the University of Maryland, Brits from Pacific Northwest National Lab and Oregon State, Ciaras from Johns Hopkins, and then this was some of the work I did when I was an undergrad as well. So if you have any criticisms, you can blame my undergraduate advisor. Well, anyways, to get straight into it, for some context about World War II, I think everyone watched Oppenheimer or Barbie, and now they're all experts on the Manhattan Project, but maybe not so much on the German project. And then the German program was called the Uranverein, and it was very different from how the Manhattan Project worked in that it was marked by a lot of cutthroat competition, personal rivalries, and fighting over very limited resources that only got worse as the war went on. The Uranverein was formed when Wilhelm Hanle actually first proposed the uranium machine. So it's only in April of 1939, 5 months before the war breaks out in Europe, that the concept of a reactor is even invented, and it was in Germany. And all the physicists, hear about this at the German conference, and a lot of the German physicists that flee to the United States carry this news all the way to Columbia and Princeton, where they tell Fermi, who had escaped Italy's fascist laws a few years earlier, that oh my God, the Germans are talking about a chain reacting uranium machine, and that's when a lot of people realize the implications of or the potential, depends on how you spin it, of nuclear power. So under the Reich Ministry of Education, they get support from a General Becker, and the original stipulation is that this nuclear program is for the creation of new energy sources for rocket propulsion. Because as far as the Treaty of Versailles was concerned, not that it mattered much after September of 1939, but the loophole that General Becker uses, is that in the Treaty of Versailles, Germany is not restricted. They're restricted in all sorts of things like producing tanks or aircraft, but they're not restricted in making rockets. So the first justification for the German nuclear program is that we're going to build rockets out of this nuclear power. And obviously, we know today that, nuclear power doesn't quite have the energy density as solid rocket fuel, but that was the hopes of the Germans at the time, at least on paper. And eventually, this German work it gets split into around four different locations. They're split between groups in Berlin, Gotha, Leipzig, and Heidelberg, and they're headed by different universities and different PIs. Basically, they're headed by Heisenberg at the Kaiser Wilhelm Institute for Physics in Berlin. Kurt Diebner actually runs an army research center in Gotha, and Doppel and Botha are working at two other universities. So it's really difficult to try to pinpoint what the end goal of the German projects were at any given time, because these competing groups were often sabotaging each other, or well, maybe not straight out sabotaging, but they gave a lot of conflicting promises to the higher ups, namely the Reich Ministry of Education and the German Army, of what their end goal was. It ranged from rocket fuel to reactors to submarine propulsion. But generally by 1942, I think they were all really focused on making a working reactor. But the recorded reason of what they were working on, the recorded goals of what they were working on were quite spectacularly diverse and optimistic. Over the course of the war from 1939 to 1945, the Uranverein in total have 2 tons of heavy water and 14.3 tons of natural uranium. And that's a good number to keep in mind as we go deeper into the nuclear forensics. So the war doesn't go, well, that's the next slide, my bad. But some of the early reactor designs are generally with uranium oxide and with paraffin or graphite moderation. And the early German reactors were coded based on B or L for Berlin or Leipzig, or G for Gotha, and then a number which, increases sequentially. And all of these projects, they do a lot of experiments, and they're generally pretty unsuccessful. And the situation only gets, sorry, that's the next slide. The Uran variant was actually ahead of the Manhattan Project until early 1942. Um, where in terms of the material produced, the Germans were producing 1 ton of uranium metal per month at a Degussa factory owned by IG Farben in Frankfurt using forced laborers. Don't ask what they were doing in 1942. They were also producing a lot more heavy water than anywhere else in the world because the only heavy water factory in the entire world was in Norway, which was namely, before the war at least, used to produce biological tracers, which was what heavy water was used for, and to create ultra pure light water, H2O, for reference sampling purposes. And the reason why the Uran Verein is so ahead of the Manhattan Project in early 1942 is that the United States only joins World War II in December 7th of 19 or December 8th of 1942 after 1941 after Pearl Harbor. So the Manhattan Project actually doesn't really kick off until mid 1942. So it's quite late in the war that the Manhattan Project actually begins in comparison to the timeline of World War II. Unfortunately, well, maybe fortunately for the Americans, but unfortunately for the Germans, General Becker commits suicide because Hitler blames him for a lack of armament, a lack of sufficient armament production, and a lack of results in the Wunderwaffen projects, including the German reactor project. And Albert Speer, the architect of the Reich, is quite unconvinced on whether the Germans could really achieve a critical reactor by the end of the war. So the army actually gives up army funding of this project and gives it back to the education ministry, but it keeps some Kriegswichtig, which is high priority wartime funding. So it gets a little complicated, but the point here is that the German project was never really consolidated under the army for the entire war with a consistent stream of funding. People died, and the project changed hands multiple times, and there was a real lack of consistency on groups working together on a singular goal. Unlike how, say, the Manhattan Project might have worked, they all gathered together at the University of Chicago and worked together at the metallurgical laboratory, or generally almost a lot of the Manhattan Project did. Yeah, that's a separate discussion that we can talk more about comparing the Uran variant to the Manhattan Project one to one if we have time at the end of my talk. But anyways, so we're at 1942, and once we go into 1943, things really start to go sour for the Germans. In January of 1943, the British and the Americans have consolidated their air forces in Great Britain, and they begin a consistent Allied bombing campaign of Germany. And what that means for the Germans is that a lot of the infrastructure starts to get destroyed. They're losing power. They can't rely on having safe or having their laboratories be intact overnight because the United States conducted almost an unrestricted bombing campaign over German cities. And in February of 1943, Norsk Hydro gets sabotaged. So this is the ship that carries the heavy water from Norway to Germany, and on it are shipments of heavy water, and it gets sabotaged by the Norwegian resistance with the help of the British Special Forces. And Germany loses a couple hundred tons of heavy water, very precious considering that, or a couple hundred kilograms of heavy water, which is very precious considering that Germany only had 2 tons of heavy water overall. And eventually, oh, I'm missing a slide here. Eventually, the Norsk Hydro plant actually gets bombed. So after 1943, Germany can't make any more heavy water, can't make any more heavy water. So it's very ironic that 1943 is when Germany actually reaches the end of its heavy water capacity in the same year that the United States actually opens its new heavy water plants to produce their own heavy water for reactor experiments. But among the different reactor projects that the Germans tried, what I'll be focusing on for specific nuclear forensics is called the B8 pile, and it was the very last one that was built, and it was built by Heisenberg, uh, and um, so this was in April 1945, when basically all of Berlin is in shambles, and he barely escapes by the skin of his life, skin of his skin, by his skin, to this cave in this remote village called Heigerloch, and he caves out a laboratory using explode. He blows up a cave, and then he builds this in the side of a cave, and it's like literally just like the side of a cave with like wooden planks laid down and some rebars for structural support. And the general gist of this reactor is that it's moderated by heavy water in the middle. It's got a graphite reflector as a jacket, and then it's surrounded by another 60 centimeters of light water all around. I'm told that we have quite a range of audiences here, from professionals that probably have been doing nuclear physics longer than I've been alive, and some high schoolers. And I'm not totally sure how acquainted everyone is with nuclear engineering, because this is week one of the nuclear engineering summer camp. But just the TLDR is that, right, you have uranium, and fission from uranium actually produces fast neutrons, very fast neutrons, 1 to 2 mega electron volts. But uranium requires very slow neutrons to fission on the order of 0.025 electron volts. So the role of the heavy water here, which is so heavy water is a deuteron, a deuterated water, so D2O, and D means that there's a neutron in the water atom, in the hydrogen atom. So a normal hydrogen atom is just a proton, right? And then a deuteron is a neutron plus a proton in the nucleus. And the difference that makes is that water, actually light water, H2O, the normal water that we drink, actually absorbs a lot of neutrons in addition to scattering it. So it slows down neutrons, but it also eats away neutrons. But what heavy water does is that by adding a neutron to the nucleus, by making it a deuteron, the deuteron actually doesn't eat any neutrons at all, almost any neutrons at all. So it has a very pure effect of just slowing down the neutrons. So it allows for a greater neutron economy and a better efficiency to the neutron fission. But getting back to the B8, this B8 reactor has 1.5 tons of natural uranium in the form of 664 cubes that are chained together with aluminum aircraft wire, and 1.5 tons of heavy water. And the reported K effective of this is 0.85. And what do I mean by K effective? K effective is just the measure of which the rate of change of neutrons in the reactor. So 0.85 means that, so we in a fission reactor we want neutrons to self-replicate, right? But if we have a K effective of only 0.85, that means that there's no self-sustaining chain reaction. So for 100 neutrons that you're putting in, it's decreasing by a factor of 0.85 every second. Well, on the order of microsecond actually, but that gets into concepts of neutron cycle, neutron life cycle, and neutron generations that I'm sure you'll cover later in the summer school. So I'll pause right here for a second. Does anyone have any questions on the history, or any clarifying questions on anything I've talked about so far? Does everyone understand what K effective is? Yeah, or am I supposed to be looking at a chat somewhere? Um, we're all good? All right.
Yes, could you explain K effective one more time?
So K effective is just say like a geometric ratio, a multiplicative ratio that tells you the rate at which neutrons are multiplying inside of the core. So if I start with 100 neutrons in the core, in the reactor core, that means that basically every second or every unit of time, the neutron population is multiplying by only a factor of 0.85. So from 100 neutrons, then the next cycle, then the next second, we only have 85 neutrons, and then the next second, we only have 64 neutrons, and then it decays by a factor of 0.85 from there. So that's what K effective measures, the rate of change. And what reactors want to do is to have self-sustaining fission. We want to have or the idea of self-sustaining is that K is equal to 1, so that the neutron population is either self-replicating or increasing in population. Moving on. So this is kind of segueing into some of the deeper nuclear forensics that I'm doing through archival documents. And the first question that I have is, how on earth did we measure 0.85 for the B8? Because if you actually think about it, a lot of the conventions, so this maybe gets into a little bit of epistemology, but how we describe nuclear engineering with the parameters and the constants and the variables that we do is actually very much a product of the Manhattan Project. And actually, like if you think about it, there's a lot of different ways you can express nuclear physics without using the same variables that we do. So what I wanted to do was to make sure, did the Germans actually measure K effective of 0.85 in this exact same way that we define K effective? And the source the source that says that the B8 reactor had a K effective of 0.85 comes from this 2009 paper by the Italians. And they say that the Germans measured a subcritical multiplication factor M of 6.7. And M is a variable that if you study nuclear engineering, you would probably know, describes the rate of multiplication in a subcritical reactor. And they say that M was 6.7, that the Germans measured M to be 6.7, and therefore we can convert it to our K effective through this formula. And this is actually a well-known formula for the subcritical multiplication factor. So this formula is true, but the question is a valuation of 6.7 actually what we call today the subcritical multiplication factor M? And if you go through the original papers, or well, sorry. So what I first study is how the Italians model the B8. And what they actually do is that they homogenize the fuel. So instead of modeling the actual chains of fuel, chains of cubes, what they model is a homogeneous mixture of heavy water and uranium that are blended together like a smushy, like a smoothie, into one right cylinder. And maybe this a bit more of an advanced topic for nuclear engineering undergrads or beyond, but uh, maybe you don't need to speak up, but start thinking through what happens if you start homogenizing the fuel in a reactor. Would you get the same K effective as modeling the real geometry? No, not quite. Fast fission. Oh, this is off the top of my head, so forgive me if I'm wrong. And there's probably tons of people that know more nuclear engineering than I do, so just pipe up if I'm wrong. But I believe the fast you actually have less fast fissions because the uranium cubes self-shield. So uranium fissions, the neutrons don't actually penetrate through the entire layer of the cube if you model the real geometry. So you actually have less fast fissions. You have a little less fissions um, than if you homogenize the reactor. And you have a lot more resonance absorption. So uranium-238, the isotope that we do not want for fission, uh, absorbs neutrons. They eat away neutrons at intermediate energies. And if you homogenize the fuel, that means that more uranium-238 is exposed and there's more resonance absorption. And what happens is that the net effect is that you end up underestimating K if you homogenize the fuel. So we already know, or I already know, you can disagree with me, that there's no way that the Italians replicated the German K effective by comparing a homogenized model to the real model, because any homogenized fuel model underestimates K. And then now we need to question what is the Italians claim that the Germans measured M to be 6.7. What is M the way we define it today actually a ratio of? Um, and what M today is that it's actually um, a representation of a subcritical multiplication. And this is a lecture topic in and of itself. But what I mean here is that when you have a K of less than 1, so let's say that the reactor multiplication K is only 0.8 in a reactor, or in this example, 0.6. What you actually end up having is that if you start with 100 neutrons, you keep multiplying, and then you actually approach a limit at which each successive generation multiplies by a factor of zero point 0.6, and then the total neutron population you actually have doesn't decay to zero, but instead you converge at a certain number. So M actually measures the ratio of the total neutron population in the reactor versus the strength of the source. So it's the number of neutrons that you end up having in a reactor versus the number of neutrons that you're putting in. But is this what the Germans defined as the ratio 6.7? And the answer is no. If you read German, you can tell me if my translation is bad or not. Well, what the Germans define to be 6.7 is the ratio of neutrons outside the vessel and not versus the number of neutrons outside the reflector n sub a. And the reason why the Italians thought that this was also the subcritical multiplication factor is that as the reactor approaches a critical size, m goes to infinity, but by the German logic, so does z. So because both numbers go to infinity, the Italians assume that they must be the same ratio. But I don't know. Maybe they didn't translate the entire report. Maybe they didn't read the entire report. It's just not. Um, 6.7 is the ratio of the neutrons at this point outside the light water reflector, versus right outside the graphite reflector. So they're fundamentally two different numbers that you can't compare at all. So the point here is that the conclusion, the sub-conclusion from here is that for almost a decade, historians have been saying there are still there's still books being written about this, and they all keep saying that the B8K effective was 0.85 because of Grasso's paper, but it's just not, because A, his model was homogenized, and then B, um, the ratio that they claim to be the German recording of of that K effective is not the same ratio that they interpreted as being. So this is one aspect of the nuclear forensics, which has been evaluating the existing literature. Now we can move on into what Heisenberg actually, some other things that Heisenberg said about the B8. So just after the war in 1947, he said in a Nature article that the material available was just insufficient to obtain a K equals 1, so self-sustaining fission in the B8. He said a relatively small amount of uranium would have probably sufficed. He also said that the critical point would therefore correspond to an increase of heavy water volume by not quite half. So later on in our work, we'll end up testing this hypothesis to see if his theory was if his predictions were correct or not. Um, but we already know from the Manhattan Project that the idea that the B8 was almost close to criticality is a little optimistic, because we can just compare it to Chicago Pile 3. Everyone knows about Chicago Pile 1, but I feel like not many people know about Chicago Pile 3. CP3 was a reactor that the Americans built in 1944. It was made out of natural uranium and heavy water, much like the B8, but it was much, much larger. So if the B8 was subcritical and it had 1.5 tons of uranium and 1.5 kiloliters of heavy water, Chicago Pile 3 had 2.6 tons of fuel and 5.7 kilotons of heavy water. So in essence, the total amount of material, if you just add this up and say, 3 tons of material versus what is that, 8.3, it's almost a factor of 2.5 more material that Chicago Pile 3 needed to go critical. So it casts a little bit of doubt on Heisenberg saying that he only needed 50% more material, when in fact he probably should have needed around 2.5 times as much material. Um, Another thing that I want to talk about the German program is another question that gets raised about, if heavy water was expensive and if it could only be obtained from Norway, why didn't the Germans also use graphite just like Chicago Pile 1? And this is often cited as a mistake, that if Heisenberg had only pursued graphite moderation, then the B8 would have worked. If he just gave up on heavy water and just made the whole thing out of graphite, then it would have worked. But it was because the Germans made a mistake in measuring the absorption of graphite in 1941 that Heisenberg made a mistake of ruling out graphite. And this myth is perpetuated quite widely, both in the Oppenheimer film by amateur historians, internet historians on Quora, or Reddit, or even semi-professional sources like the article, or even the Nuclear Museum in Germany. Or sorry, this is the American Heritage Foundation. So professional historians keep perpetuating this myth that there was this mistake to use heavy water instead of graphite. But if you look at the historical documents, you'd see that the Germans did accurately quantify boron impurities in graphite. And a mistake that we've been making in analyzing the German data is that we've been applying our definition of thermal neutrons improperly, like retrospectively, onto German experiments. I realized that um, we probably didn't cover what thermal energies are, but if neutrons have a spectrum of energies, does everyone see my annotate? Do people see my annotations? I'm guessing, yeah. Okay. Uh,
Yeah,
we
that's good.
generally consider we generally consider anything above 1 MeV to be fast, and anything below 1 EV to be thermal, and then everything in the middle to be intermediate. But within the thermal energies, we actually say that the real thermal distribution of particles traveling in free space should follow a Maxwellian distribution. So this is a Maxwellian spectrum of how we define thermal energies today. So we say thermal neutrons are particles or neutrons at a mode of 0.025, so the highest probable energy, distributed by a Maxwellian spectrum. And that was not actually how the Germans conducted experiments. They said neutrons will never totally thermalize in paraffin or any moderator. So we're going to normalize all of our data at 0.067 eV. And the problem that occurs from this is that we end up misinterpreting the German data because we expect the German definition of thermal to be our thermal. But if you conduct their experiments and then you look at the results of the neutron distribution in their experiments through simulations, you can verify the fact that the German experiments did not occur at our definition of thermal energies. So later on, you'll probably cover something called the 1 over V law, and then you'll understand, you'll probably learn, if you don't know already, how the distribution of energies affects reaction rates and absorption rates. So how you normalize the data affects how you measure absorption. So for the long while, we took at face value. So this is what the Germans recorded for their value of absorption in their graphite, which was 7.5 millibarns of absorption. And for the longest time, for almost what is it, like 7 decades, we've been saying, oh, historians have been saying, oh, they recorded an absorption of 7.5 millibarns, and that's not so different from the absorption in the graphite used by the Americans in Chicago Pile 1. So they could have used graphite in their reactors too. But once you understand that the German normalization of data was different, then you can renormalize the data and then see that the real absorption for German graphite in our definition of thermal energies was actually 12.1 millibarns. So it's actually, based on our metrics, twice as absorptive as Chicago Pile 1's graphite. Let's clear all my drawings. I hope I didn't belabor the point too much. I want to make sure it's being understood by everyone that might have not necessarily learned about absorption experiments or absorption reaction rates yet. But moving on, there's another peculiarity in how we interpret Norwegian documents, in that when the Norwegians calculated shipments of heavy water, they actually normalized all of their values to be equivalent to 100% deuterium, heavy water. So what I mean by that is that they had raw liters of that they produced and the heavy water purity of that sample, and then they normalized it to be the equivalent volume of 100% heavy water. And a lot of historians actually didn't bother looking into the original Norwegian documents either, because after so many decades, there's a lot of like circular reporting when secondary sources or tertiary sources only cite other secondary sources and not primary sources. So what happens is like this long game of telephone where people kind of stop checking the primary source, and simplifications or mistakes that are made in one secondary source get perpetuated throughout the decades. So this is actually a mistake in a lot of historical sources that they overstate or that they underestimate how much heavy water the Germans had because they didn't realize that there was this normalization process that the Norwegians were doing in their primary in their original reports. If I clear my drawings again. So redoing, so I went through all the original documents that the Norwegians had about how much heavy water they produced during the war, and we can recalculate it to be around 1.8 ton or 1.8 tons of heavy water, or around 1,700 liters. And for the longest time, we also believed that the heavy water used by the Germans in the B8 was lost. So Grasso's analysis have been using 95% assumed purity of heavy water. But while I was working for NIST for 2 years, I happened to get in touch with a professor at the University of Maryland, Tim Koth, and he actually pointed out to me that at NIST there were these jars of heavy water that we collected from the B8 experiment after the war ended, and we shipped them back to the United States. And NIST actually conducted their own purity analysis of the B8's heavy water. So NIST actually holds samples of Nazi heavy water that we can refer back to for exact numbers on their purity. So if we put all that together, oh, another measurement that we did at PNNL for this work is that we got hold of a uranium cube and then we actually measured the density to discover that it's quite porous in the inside. So it's got a density of 18.5 and not a nominal density of 19 that you might expect from metallic uranium. And once we put all those together, we can conduct our own criticality calculations of the B8. And by criticality calculations, I mean reconstructing the B8 in MCMP simulation software exactly the way it was built, and then calculating the neutron multiplication rate inside of it to see if the reactor would have been functioning, or at least how far off it was from it. Um, this is a typo. It should say, I don't know why this image is an old one actually. I thought I updated it. But it's the fiducia model, which should be the original model. And then we also can do some calculations using a spherical homogeneous approximation for some theoretical calculations of buckling and the predicted critical size, which you'll also learn if you study nuclear engineering. Um, so if we run it through MCMP, oh, here it is. Um, Sorry. So we run it through MCMP. And then we also conduct something called a unit cell model. So what we're conducting here is that we can break down K into component variables of epsilon for fast fission, for the amount of fast fissions that are occurring, P for the amount of resonance absorption, F for the thermal utilization, and then eta for the fuel utilization. So the thermal utilization tells us of all the neutrons that are being absorbed in the reactor, how much is it being absorbed by the fuel? And then eta tells us of all the neutrons that are being absorbed by the fuel, how many of it are actually causing fissions. Um, so we constructed a Wigner-Seitz unit cell model of a B8 cube, and then by giving it reflected boundary conditions, we can essentially create an infinitely large reactor. Because as far as the program is concerned, any neutron that leaks out the surface is actually coming straight back in. So this is equivalent to having an infinite lattice of identical uranium cubes all around the model. Does that sort of make sense? If it doesn't, you can ask Flynn. I think he's much better at explaining these concepts than I am. Um, so so what we end up doing is we calculate the criticality of the original B8 as it was built to be 0.947. And this is significantly different from what Grasso claimed, which is 0.85. And we reached this conclusion thanks to all the nuclear forensics that we did to create a more accurate model of the B8. And what we do next is that we create something called, how do I go back? We create something called a spherical model. So what we're doing now is that we use something called hexagonal close packing. So we so we want to run an optimization now. So we calculated the original criticality. And now we want to ask the question, how much more fuel and how much more moderator would be necessary for the BA to actually work? And the minimum critical dimensions, the critical materials that we calculate is around 4 tons of moderator and 3.5 tons of fuel to get a K effective of 1, which is when we get self-sustaining fission. And the way we do this is that each of these points on this data plot represents a model that we constructed spherically. Um, and then we automate this process. So if we can use something called hexagonal close packing, which you might know from material science, hexagonal close packing is the densest configuration of points circumscribed by a larger sphere. And by increasing the radius, we can, by making it a sphere, we can collapse all the dimensions of the reactor into just one radius. So as radius increases, we have the hexagonal close packing formula to tell us the distribution of fuel. And then we calculate the amount of fuel and moderator that fills out that radius. So does that make sense? So for this optimization here, we're actually making everything a function of radius, and then we're increasing radius and then tracking how much more moderator and fuel that's being added until we get a criticality of 1. So to go over some of these results, oh my God, I should delete these annotations. We get that for around 1.8 tons of moderator and 5.5 tons of uranium that Heisenberg had available to him by 1945, he needed actually around 2 times more moderator. And with this, we can conclusively say that his prediction in Nature that he only needed 50% more moderator was off by a factor of a little bit more than 4, and that this B8 was nowhere close to really being critical. And this kind of describes the extent of the German nuclear project, that this is as far as the Germans achieved in April of 1945, and then the war ends on May 8th of 1945. And there's a lot of speculation out there of, how close were the Germans to making a reactor, or what if Germany actually made a working reactor, made a bomb? Well, my study, or our study, basically shows that the Germans we quantify how far the Germans were away from criticality by analyzing a lot of the primary sources and then kind of cutting and reading between the lines of secondary sources, right? We cut through the secondary sources, we go directly to the primary sources. We read the original German of what Heisenberg wrote, we translate them ourselves, and then we reconstruct the nuclear engineering straight from the primary sources. And I feel like that kind of reduces or kind of answers all the questions that people might have about how far the German nuclear project got. So I kind of want to end my talk for now, maybe a little early, 5 minutes early, on what Heisenberg on the fact that Heisenberg did understand, at least in theory, how to make a nuclear weapon. So people might surmise that if Heisenberg never figured out how to make a working reactor, did he even know how to make a bomb? And this diagram actually shows how uh the left diagram is actually fast fission. Or sorry, this is fission in normal uranium, in natural uranium, where there's only 0.7% of uranium-235. And on the right side is his diagram of how fission would occur in pure uranium-235 without any moderator. And right here, he's showing the fast fission process for detonating for getting supercriticality or prompt criticality or prompt supercriticality out of a highly enriched uranium-235. And with that, I'll take any questions or any concerns that the audience might have about my nuclear engineering.
Yeah, thanks, Patrick. That was a great talk. We do have plenty of Q&A questions.
Oh, I
so
see. I need to. Okay.
Those will surely keep us busy, and don't worry, I can help organize those for you. Just to start off, thank you for bringing layman's terms involved, like with the criticality explanations. I know you said I could explain like some of those models, but I would actually hazard, I think you would be better at explaining some of those points, but I'm happy to help where you think it's appropriate. let's go ahead and dive in. We also have some people in the room that have questions. So I'm gonna go to theirs first.
Sure.
Oscar has one. When you go back to the graphite material definitions, right, and the capture cross sections, Oscar is asking what would cause the absorptions of the two graphite sources to be so different? Was it just impurities in the materials, or what was the fundamental reason for that difference? You showed the energy spectrum, right? But then when you reevaluated, these values are so different.
Uh, could you repeat that? Sorry.
Yeah, what just causes this difference as a whole, right? Like you show for the Chicago pile graphite, the absorption cross section to be nominally about 6 millibarns, right? And then for the German reactor, right, initially they were estimating about a little over 7 millibarns.
Mhm.
But then if you correct it with your explanation you showed here, it changes quite significantly. Like what's the fundamental reason? Are these different types of graphites? More specifically, like why are these so different?
Oh, um, there's a long historical reason too. But Chicago Pile 1 graphite was actually produced after some purification process. So if you do a deep dive into graphite, you'll come across something called Acheson furnaces, uh, Acheson furnaces, which was how everyone made graphite by purifying petroleum coke or by burning petroleum coke. But the American furnaces could go up to 2800 Celsius or 2800 Celsius. And the German ones could only go up to 2500 Celsius. And this difference actually made a difference in whether or not they could burn away boron monoxide uh, that was dissolved into the petroleum coke. So because American furnaces were at a higher temperature, they were generally more pure. Um, which is why there was a difference between 6.5 and 7.5. And then the difference between 7.5 to 12.1 comes from the fact that this cross section at 7.5 is evaluated at 0.06, whereas at 12.1 millibarns is when we correct it for the evaluation at 0.0253.
Got it. That makes a lot of sense. Thanks for that
Mhm.
detailed explanation, Patrick. I think we had one more in the room here.
Sure.
Yeah, Aaron asks, what do you think about the hypothesis that Heisenberg was deliberately impeding the German nuclear program?
Oh, I think um I have papers coming out on this. I think I tried to avoid any political commentary on what Heisenberg might have been thinking. Um, it's certainly true that I think there's a lot of merit to the argument that a lot of it was just hard copium after World War II, as the youth say. Um, because actually in the paper in the Nature paper where he makes these claims, he actually circulates a draft of this where he like originally like really just like throws a few physicists straight under the bus and they read the draft and they're like, we are not letting you submit this and we're gonna like fight you. So this draft, there's actually multiple drafts of this paper. And Heisenberg actually has to rephrase a lot of the wordings on why some things didn't work out. And he ends up blaming the German army for some things that he originally blamed a couple specific physicists for. Um, so I think there's a lot of historical revisionism after the fact. But I thank you for the question, Aaron.
Yeah, that was a
Uh,
great one. Thanks, Aaron. We have tons in the chat.
sure.
So I'm gonna start scanning through them. You may as well. And if you find anything interesting, feel free to answer it. But I'm gonna try and filter out a few interesting ones as well.
Oh,
But yeah, if you
some of them I can actually breeze through. Aditya's first question, how did the Germans acquire natural uranium ore? It was dug up in Czechoslovakia. That's where a lot of the natural uranium mines were. They used a lot of forced laborers. So that's an unethical portion of the German nuclear program. Why cubes? Why not any other shape? Heisenberg actually used plates because he found them easier to calculate on hand, because that way your diffusion equation, all your calculations are only in 2D. But Diebner actually wanted them to be cubes, to be three-dimensional. But then if they're cubes, diffusion from a cube is slightly easier to calculate because it's isometric. Is it possible to provide references? I can give you an archive reference. for some of the paper for some work coming out of it.
Yeah, Patrick, as far as references go, if you want to email me after, we can share that with the group.
Sure. How does the criticality reactor come in? I only hear K effective. K effective is the criticality of the reactor. Um, Criticality means K equals 1. Supercriticality means K is greater than 0. What is this B8? Hopefully you learned a little bit more about the B8 by the end of the talk. Um, Why do Germans use natural uranium rather than use enriched uranium? Oh, it's because Germany didn't have the facilities to enrich uranium. So it's a little unfair to compare the American program with the German program, because if you actually look at, so we only really talk about Chicago Power 1, but the Americans pursued graphite moderated reactors, heavy water moderated reactors, light water moderated reactors with enriched uranium. They chose all the paths. It just happens to be that Chicago PAL 1 worked first, but Chicago PALs 1, 2, and 3, as well as a few PALs at Los Alamos, they got criticality with all the different ways, including with organic moderators and organic coolants too. So yeah, I like it's rather actually unfair to compare the scope of the Manhattan Project over the German one. Also, the German one really went down, the German program really went downhill after Stalingrad. So basically, all of the physicists that were aged like 25 or younger or 30 or younger, or even nuclear physicists, they were just straight up drafted as privates into the German army and sent off to the Russian front. Um, so they actually lost a lot of young talent. And there's an argument that by Manfred Popp, he was a director of West Germany's nuclear energy program in during the Cold War, and he wrote that because the Germans drafted all of their young physicists, a lot of the young physicists had actually studied at the University of Michigan or Berkeley, where they had worked on cyclotrons in the 1930s. So they brought back knowledge of the cyclotrons to Heisenberg's group, but Heisenberg actually was really like reluctant to pursue like experimental physics, like new experimental physics, because he was like a pure theorist. And the division between theory and experiment in Germany was a lot more insanely divided than it is in the United States. So basically, he dismissed the idea of the cyclotron or building any cyclotron. And the problem is that the cyclotron was actually used to synthesize plutonium for the first time in the lab, and that's how we first analyzed the nuclear properties of it in the lab at Berkeley through their cyclotron. So the Germans never had the opportunity to study cyclotrons, basically because they drafted all the young physicists that had learned about the cyclotron that when they were studying in America. Um, could you please elaborate on the subcritical multiplication factor? How is it different from K effective? Unfortunately, you're gonna have to seek another lecture on that. Maybe during the summer school. Will you be covering that, Flynn? Will
One
you be
moment, yeah,
covering?
I just want to make sure I didn't get some feedback. Yeah, I'll talk a little bit about criticality
Mm,
in our keynote neutron talk in a couple weeks. But yeah, that's less of the focus here. We're focusing more on radiation detection throughout the lectures. There's
mm,
plenty of online references if you want to learn about criticality. Patrick gave a nice explanation as well earlier in the lecture, so focus more there. But yeah, if there's any resources, feel free to reach out individually if you want to be directed.
sure. Another anonymous attendee asked, the problem was wrong assumption of energy range thinking American metrics to be universal. Yes. Because of the prevalence of the Lamarche's text of Lamarche's nuclear engineering textbook, I would say it is more universal than not today. But I think the real upshot is that you need to be really careful about like what conventions you're applying from the United States to elsewhere. And if there's any foreign physicists in the room, maybe they can pipe up on some differences that they might have experienced between how nuclear engineering is taught or codified in the United States versus maybe in the Middle East or in Asia or Europe or something like that. Um, any takers on that? Or maybe not. Um, Aaron asked, is 0.067 still within the energy range of thermal neutrons? Yes, this is where it's actually really confusing. So there's three different ways of how we define thermal energies today. Let's see, maybe I can just use the blank spot here. So the first definition is neutrons of any energy below 1 electron volt. And the second one is neutrons at exactly 0.0253 253 electron volts. And then the third definition is the Maxwellian distribution, modal at 0.0253. And even though they seem very close, if you work out the math for their absorption reactions, you get very different results. Probably because absorption as a function of energy and cross section is 1 over v, and it's 1 over v logarithmically. So if you put it on a linear plot, it's actually like like a very steep curved plot. So even small differences in energy can mean significantly higher absorption. Um, and as for these 3 definitions, it's just really confusing. We just have 3 different conventions. This third one is technically the most accurate when we're evaluating cross sections. This is how Brookhaven evaluates other thermal cross sections. The second definition is like the most technical definition of thermal, because this thermal means equilibrium at 20 degrees, like at room temperature. And so room temperature directly translates to 0.0253 electron volts. And then the first definition is just almost a shorthand when we're doing hand calculations. Um, uh, Julio asked, did the lack of neutron thermalization result from the small size of the reactor or the absence of graphite within the reactor? Um, there wasn't enough thermalization in the B8 because the cubes were too close together. So there wasn't enough heavy water in between them for the neutrons to purely thermalize. So in our criticality optimization, we saw that if you actually spaced out the cubes more, even without changing anything else, if you change the spacing of the cubes to be wider apart and make the tank slightly wider, then you increase criticality. But the Germans couldn't do that because they actually recycled the tank that they built the reactor in that held the heavy water, and they couldn't get another tank machined in April of 1945 when Berlin was being bombed to bits. Um, what does it mean, 98.6 heavy water? It means that for 100 molecules of water, for 100 molecules in the moderator, 98.6 of them is D2O, and then the other is light water, H2O. Um, So the graph only works for this model, right? If I were to generate a similar graph for an SMR, theoretically or by simulation, what process would be suggested? Um, I feel like that's a question from a professor. That sounds like a question a professor might ask. I'm guessing they're talking about this graph, right? So this is only true for our model. I would say you can do. Lamarche has a good plot where he plots. Um, And normally plots are have the moderator to fuel ratio on one axis. So this is atoms of moderator per atoms of fuel on the x-axis. And then they model critical size versus critical mass. And then they find the optimum, I think, through comparing critical mass versus critical size. This is in Lamarche's nuclear reactor theory, chapter 7.9 or something like that. I was just looking at it and I was thinking, oh my gosh, should I make this for the B8? But I'm kind of lazy. So there's the real answer. How are we doing on time, Flynn?
Right, yeah, we still have 7 minutes left in our budget. I'm gonna cut you off at 2 p.m.
Mhm.
But yeah, great job going through all the questions.
Sure.
There were, I think, um, yeah, a few more questions. I'm trying to just filter out some that might be more interesting to the general audience. There's one question here, how the Germans calculated their criticality, right? Like
Oh,
what's the comparison there? You explained well how you were calculating it with your model, right?
mhm. So
But what
K
are
is the
the,
American model of the Germans actually use something called um they called it the multiplication factor, but it was actually a weight of the amount of fast fissions multiplied by the leakage multiplied by the neutron velocity, the average neutron velocity in the reactor. So it's basically our K infinite, but multiplied by the neutron velocity. So it wasn't too different, but the main difference is that they didn't account for, uh, sorry, I'm blinking here. there's one thing that they didn't account for that we account for in K, but I forget exactly what it was, but it's very similar, but a little different. Uh, Maybe I can take a brief moment to talk about North Korea, but maybe that's a little ambitious.
Yeah, Patrick, feel free to talk about your research if that's what you prefer to end off the lecture. We have a lot of questions here.
Mhm.
I think if you want to talk about that, we'll go ahead and end the Q&A session. I know
Oh, sure.
several of you have questions online, but yeah, please go back to Patrick's recording. That may help clarify a few of your questions. We'll post that online by the end of the week. And sorry we can't get to everyone here. We appreciate all of your interest and all of the great questions, but unfortunately we don't have the time every day to go through all of these questions. But yeah, Patrick, please take it away. Tell us a little bit about your research for the satellite reconnaissance on North Korea.
Oh, this will just be a little casual talk. But I've been at Princeton, we're working on visual and IR imagery of North Korea's experimental light water reactor. So, well, I also like to call this keeping up with the Kims. This is the end of semester research presentation I gave to my cohort. So this was like when we're just like doing shots, and this was very casual with my cohort. Um, but anyways, to get a little more serious, in October actually, they've North Koreans. So all of the reactors in North Korea are located at the Yongbyon Nuclear Scientific Research Center, which is slightly north of Pyongyang, and they have one working 5 megawatt reactor that they got from the Soviets that they've been operating since 1986 to today. In October, we noticed on satellite imagery that they had apparently finished construction of this reactor and began operating it between late October to early November. So it's this reactor right here. And visually, it looks like if you look at the dome and then the square building, and then there's like a pipe here, it actually looks very much like a VVER reactor, just a containment housing, but we can't be sure. If anyone else has any ideas, you can pipe in. But we also got access to some thermal imagery through a British company called Satvu that actually is doing something called high resolution IR imagery. So the problem with IR imagery right now is that commercially the only available resolution is what, like 30 meters or something like that. So that means that every pixel is 30 meters. Um, but the Satvu company is claiming that 1 pixel on their imagery is like 10% of that, so 3.5 meters. So this is the best resolution thermal imagery that we have on the market so far. And then Princeton and Stanford got some access to it um, for some research purposes. And what we noticed was that there's hot water coming out of the ELWR, which is how we figured that it was operating, because through visual imagery we saw that North Koreans were digging up a pipe from the reactor to the river right here. We have imagery of them digging up a pipe and laying the pipe. So we know that that pipe is connected. And if it's hot water is coming out, we're assuming that it's from hot, maybe secondary water. Um, so by tracking the hot water, we estimated that it was around 167 days of operation. And if you run the burnup calculations, it kind of gets to be around. So we know that this is 100 megawatts thermal, because the North Koreans publicly declared it, and then a Stanford professor, or he was the director of Los Alamos at the time, Siegfried Hecker. He traveled to North Korea and then verified some of the specs of this reactor. So we know it's 100 megawatts thermal, around 33 megawatts electric. If it was operating at full power for 167 days, then we can kind of estimate that there's around 7 kilograms of plutonium made. And then Stanford has a little more conservative estimate, around 6 to 20 kilograms. Um, and I think we believe it's a Soviet VVR class reactor. They say so the special thing about this is that it's marketed as an experimental light water reactor, and that's different because North Koreans have only been using natural uranium graphite moderated Magnox reactors. And the interesting thing is that to make plutonium, I'm assuming that people that are sticking around are more experts on nuclear engineering now. Right, you want natural uranium. You want to maximize uranium-238 and minimize burnup to make plutonium for separation purposes. But North Korea actually, Kim Jong-un made a few speeches saying that North Korea needs to utilize more renewable energies because they're maxed out on coal mining. So they need to make use of resources like nuclear and solar and hydro, which I didn't expect the North Koreans to be trying to make, but they're doing that. So they're explicitly marking this as a light water reactor that uses slightly enriched fuel. And in that case, enrichment gets a little different, or plutonium separation gets a little more challenging because you can't really get as good plutonium production from slightly enriched uranium versus just natural uranium. So we actually think that they're either using this to breed lithium-6 to make tritium for thermonuclear weapons, or they're using driver fuel to have an outer layer of natural uranium and an inner layer of slightly enriched uranium to make plutonium that way. So we're doing some neutronics for this, and then we're continuing to observe the ELWR through satellite imagery. And then the most recent thing that I'm working on is something called synthetic aperture radar. And what that basically means is that man-made objects light up differently because they have different reflections from radar. Basically, shiny things reflect more. So we can see power lines. They kind of look chromatically in synthetic aperture radar. And what I've been doing is trying to trace power lines from the ELWR. This is a power station right here. And if I can't share SAR imagery just yet, but they actually go, so this direction is north. They go north a couple kilometers and then they go into the dirt. And then we've been trying to create a machine learning model to scan North Korea to see where the power lines might pop up. And then we can reconstruct where their nuclear power is connected that way. So that's a quick gist of the work we're doing, the current work we're doing at Princeton regarding satellite monitoring and verification through these remote means. Sorry, I went a little over past two.
That's perfectly fine, Patrick. That was super fascinating. Unfortunately, we are tight on time here, so I'm gonna have to close the webinar. But thank
Sure.
you so much again for your talk, Patrick. It's been great. We're gonna post the recording later, and I hope you do register on that form if you have the link. If you don't, I'll send it via email again. But yeah, thank you so much for having a great second talk on the summer school today. For anyone that's still on tomorrow, we're going to be talking about safeguards by design, and we're going to have Dr. Shaw from Oak Ridge National Lab talking about how we can better implement safeguards inherently in new reactor designs and in the current already deployed reactor designs. So looking forward to that. We'll see you all tomorrow. And thanks again, Patrick. See you.